So at Allozymes, we use nanopore sequencing mainly to understand our libraries. So here's a very simple illustration. You can see we have a pre-sort library, which that could be a million of different variants in there. So after microfluidic sorting, we'll enrich what we call a sorted population. We call it a post-sort pool. So in this pool, we'll have only limited number of variants that has better activity. So how do we understand this? So using sequencing, we develop in-house wet lab and dry lab workflow to understand the whole the complete gene sequence. So we can understand the exact sequence of every single gene of interest inside a pool. Using our wet lab method and dry lab method, we can decipher up to 1 million DNA molecules inside a pool. So by understanding all these information, we can understand individual sequences, and we also calculate the variant occurrence inside our library, pre-sort or post-sort. So how do we do this? Let me show you this very simple examples. So here you can see in a pre-sort library, I'd say it's a scanning library, we have a parent protein sequence here. It's a 10 amino acids illustration. Here we have example of 4 variants. We have, each of them has 1 mutation, so A, C, H, D, 4 variants. So in here, if you look at this yellow variant, the H1, the H variant here, so let's say if this variant has high activity, we can say enrichment in our post-sort pool. So in the pre-sort pool, we'll say this variant has 25% of the population, right? So it's 1 out of 4. When we get into the post-sort pool, we can say it's 70% of population. It's 3 out of 4. So 75 divided 25, the enrichment factor is 3. So this is kind of how, the general idea how we calculate enrichment in our sorting. So how does it work out in the real life? So here is an example of a real data and an enzyme with 300 positions. So each of this, the columns are positions, so 300 of them. And the y-axis is substitutions. So remember, we have 20 amino acid. If we don't calculate the wild type, there are 19 possible substitutions. And each tile in this heat map indicates 1 unique variant. Okay, so here you can see the percent population of each variant ranging from 0.004% to 0.129%. And it's mostly homogeneously distributed. The median of these populations is about 0.2%. 0.02%, with some a bit higher. But here is our input library. You can see it's a pretty good quality. We cover the whole sequence space. So after sorting, here's our result. You can see there are a lot less variants in our sorting. That means we already weed out all the non-functional one or low activity ones. So here what we're seeing is after activity sorting, we're enriching the winners of this particular activity that we're looking for. Again, you have x-axis of different positions, y as different substitution, and the highest population percentage or highest enrichment factor calculated. In the end, we have 1 winners. And here we down select from 6,000 variants down to about 100. So we can carry out follow-up different validation tests to really understand the activity of these variants and pick the final winner. So this is based on our pool sequencing result. We can also do clonal sequencing. So we have in-house workflow to do high throughput clonal sequencing up to 8 times 96 well plates. So using this method, we can identify the sequence, the variant of each individual wells, and link it up to the functional data. So it could be plate-based method, fluorescence, absorbance, or HPLC data. We can do high throughput HPLC as well. So by combined sequencing and HPLC data, we can input all these information into our machine learning model and to help us predict next round of improvement.